So at this point, you guys should have tablet turned on, Microsoft Teams fired up. Everyone on their Teams screen should have a 1-IBSL tile. Is anybody missing that tile? Yesterday I preloaded the roster in, so it should be there for everybody, but I have to do it manually, so sometimes you miss a name or something. Or you pick the brother or sister on accident because you're going fast trying to like bang this out. Okay, so go ahead and click on that. Then you click on class notebook. It takes a minute for that to populate. Right, like mine's taking a second. It starts coming through. Okay. Once it's through, you're going to look for this drop down here. Mine says editing. I think yours says viewing because I made this. You'd have different options. But you just pick open in desktop and that'll load this new notebook into your existing OneNotes. You're welcome to close your notebook from last semester so it's out of the way for you. You don't get confused and look in the wrong one. All the notes and everything from first semester is in the second semester notebook still, so you don't have to worry about that. Everything, I just ported it over, so everything from first semester is still there. On occasion, when you load this in, it may not come through right away. So in that case, if you do your drop down here and click on more notebooks, sometimes it'll be in the list here that you have to open it manually, but most of the time it loads it through. I forgot to close my notebooks from last semester. How's everybody get that figured out? You've done this before a couple of times, I think, at this point. What? So if you click the viewing drop down, so it should be so it should be up here in the right hand corner. Hi Lucy. I guess that was the one you're going to pick. Kevin, did you find it?
Yeah, I found it.
Okay. All right. So setup will be the same as last semester. So like everything that we're going to be doing goes into the minor ordain. I ported over all the links from last semester, so those are all there for you, as well as like all the announcements and the syllabus and everything there is in. This should all look basically the same as last year or last semester. The grading scale and everything is the same. The syllabus is the same. I'm not going to go through any of that separately. Is that okay with everybody? Because we're all in here last semester. I'm the same teacher. It's the same story. Everybody good? Okay. If something comes up and you want to talk about it or have questions about it, feel free to let me know. But in the meantime, I'm going to fire up the new stuff here, and we're just going to kind of hit the ground running. That didn't do what it was supposed to be doing. Of course not. Why would anything work the way it's supposed to on the first day?
No, but we gotta see. We're in like a country club. My shoes don't worry about it. Oh, our is a couple over. The restaurant.
Oh, whatever. All right. Our plan here, we're going to start by continuing our discussion of probability. This time, though, extending it to situations where perhaps there are infinitely many things in our sample space, which is going to require kind of a different framework to deal with. So we're going to start by introducing some new vocabulary and some new notation. So the first piece of new vocabulary is called a random variable, which differs from a variable like in our algebra classes. So random value is a quantity whose value depends on chance. And there are two types of random variables. There's discrete random variables. So a variable that takes on only a finite or countable number of possible values. So example of a discrete random value would be like the which side of a dice you roll, right? Like a 1, 2, 3, 4, 5, or 6, right? There's only 6 outcomes possible. That's countably and countable and finite. So you could have, when we say countable in math class, what does countable mean?
You count.
Well, it means that you could write or create a function that maps that set onto the counting numbers, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So like you have the number line, and you have the integers like -1, 0, 1, 2, etc. Those are countable. If you have the real numbers, like the decimals, the entire real line, not countable. That'll be the next category, right? So the other category of random variable we have are continuous random variables. And that is a variable that can take on any value within some interval. So a continuous random variable is the set of real numbers or some interval on the real number or on the real line. So like all the values between 1 and 2, there's infinitely many of those, uncountably many numbers between 1 and 2. Everybody's okay with that? Okay. So just like grinding through some vocab and clarifying some ideas. So some examples. So let's say B represents the random variable that's equal to the number of babies in a pregnancy. Is this discrete or continuous?
Discrete.
Discrete, right? Because how many babies can you have in a pregnancy? 1, 2, 3, 4. Yeah, maybe 5. Right, like in theory that can go up. That can go up, but it's not going to be. You can't have 1.1 babies or 1.05 babies, right? There's fixed number. Now, is there an upper bound to that? Like, well, there's only been, like, there's, it depends if you're talking about humans or not. But like in human history, like the number of babies in a pregnancy, there's some record for the number, whether it's 10 or whatever, which is a crazy pregnancy, ladies. You have that to look forward to possibly in your life. Let's take another example here. M, the mass of chips in a packet. So like you have a little bag of chips, you weigh out the mass. That's continuous, because depending on how accurate your scale is, the mass of chips could be 10 grams, or 10.1 grams, or 10.01 grams, or 10.001 grams, all the way down to like as good as an instrument as you have, you can measure that to any number of decimal points you want. Does everybody feel okay there?
Yeah.
Okay. T is the time taken for a runner to complete a 100-meter dash. Continuous. X is the number of sixes obtained when a die is rolled 3 separate times. Discrete, right? Everybody feel okay?
Yeah.
Okay. Oops. Just did that. So, in order to discuss probability, all probability basically boils down to counting. So our first order of business is going to be trying to figure out or count how many different ways an event can occur. And after we've done that, we're going to want to build a probability distribution or a probability model. So just like in chapter 8, we can talk about a probability model here. That's just listing every possible value for the random variable and the probability that each one of those possibilities occur. So it's just kind of enumerating everything out. What are all the different things that can happen and the probability that that event could happen. I should say outcome, not event. So again, the same idea as the probability again, just like in chapter 8, the two things you require, you need the entire sample space and then the probability for each outcome, just like we did in chapter 8. So let's do an example here of building a probability distribution. So our situation is we're going to roll 2 dice and we want to find the sum of the resulting rolls. Okay, so just like Monopoly or craps or your board game of choice, where you're rolling 2 normal 6-sided die and adding up the spots on the 2 die. So our random variable is going to just be the sum of the dice, right? That's going to be our random variable. We'll use the capital letter X to represent that. We use a capital letter for the random variable. So there's lots of possibilities. When you roll 2 dice, what are the different possible rolls we can get? Not 1 through 12.
1 through 12? How do you get 1 through 2 dice? It have to be 2 through 12.
2 through 12, right?
Oh, yeah.
Everybody's okay?
1 through 12.
No dice have 0. Not the dice we're rolling.
Yes, you're hating.
So I want to be clear here because the notation can get a little sticky, and this can be hard for students. So X, the random variable, is the sum of the 2 dice, right? The event or the outcomes in that random variable, the different values X can have, are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That those specific individual outcomes we're going to represent with a lowercase letter x. Okay? So when x is equal to 2, we have 1 roll that can happen when we roll a 1, 1. Everybody's okay? When x is equal to 3, we have two different rolls that can happen. I can roll 1, 2 or a 2, 1. When x is equal to 4, there's three different rolls that can happen. A 1, 3, a 2, 2, and a 3, 1. What's that? Yes, like Pascal's triangle. Yeah. Is everybody okay with this? So in my diagram here, the sample points, these are the individual outcomes, right? And f of x is the number of outcomes in that event. So lowercase x is equal to 2 is the event. 1, 1 is the outcome. And f of x is the number of outcomes for the event x equals 1. Is everybody okay just kind of rehashing this vocabulary? Okay. Everybody feels clear? I know event, outcome, random variable, like the notation and the vocabulary can get rough the first time through. That's why I'm trying to be specific and really trying to hammer away at that, because communication is important, right? All right. If we're going to try to find the probability for our random variable x, which in this case is going to represent a different example. This is going to be the number of 6s obtained when a die is rolled 3 separate times. So P of x equal to 0 is going to be the probability of rolling the dice 3 times and getting 0 6s to come up. Okay? So P of x equals 2 is going to be the probability that we roll that dice 3 times and 2 6s come up. If we say the probability that x is equal to x, means we're looking for all possible outcomes and the associated probabilities, also known as the probability distribution. So, to help build this probability model, I'm going to create a tree diagram. So if all I care about is if I rolled a 6 or not, I'm going to have 2 different outcomes. I'm going to have 6 and not 6. Everybody's okay? Rather than doing 6 and then 1, 2, 3, 4, 5 as 6 separate branches on my tree, that's going to get real rough real quick and more work than I need to do. So far, so good? Yes. Okay, so this first branch represents the first roll, the first dice that's rolled. What's the probability of getting a 6 on that first roll? 1 out of 6. And then not a 6 would be 5 out of 6. Because those two probabilities should sum to 1. Everybody's good? Yeah. Now we're going to add the next branch, which would represent roll number 2. So if I got a 6, I roll the dice again, I either get 6 or not a 6. If I started at not a 6, I roll the dice again, I either get a 6 or not a 6. And then I have to roll a third time. So there's like 3 sets of branches, right? There's roll 1, roll 2, and then roll 3. Does everybody feel okay? So what I would do next is I'm going to calculate the probability down each one of these branches. So if I look down this first set of branches, what is this going to represent the probability of? 6 and 6 and 6. When we calculate probabilities, if we use the word and, does and mean multiplication or addition? Multiplication. So to calculate the probability, rolling 3 6s, it's 1/6 times 1/6 times 1/6. Everybody's good? If I look at the next branch, I rolled a 6, and then not a 6. Okay? That's the probability of rolling, one way of rolling 2 6s. Is there going to be more than one way of doing that?
Yeah.
Yes. So what I'll do to calculate this one specific event, again, is I'm going to just multiply down 1/6 times 1/6 times 5/6. But then I'll need the other ways that I can roll 2 6s, for example, 6, not 6, and 6, and have to add those up, those probabilities up, to get the probability of rolling 2 6s, because there's lots of different ways that that could happen.
So if it asks for like a specific number of 6s, then you can go if you're going to get all the ways you can get 2 6s.
Correct.
Okay.
So if we want, we'll sort this in a second. But if I want the probability of rolling of x equals 2, that means I have to find all the ways I could roll 2 6s, add up all those probabilities, because these are all the outcomes in the event rolling 2 6s.
So would you list them first and then like circle what ways you can get the 2 6s?
I would not try to do it all in one shot, at least not yet. Eventually we'll figure out how to do it shorthanded and make it a little bit easier, depending on the situation. But for now, yes, if I'm drawing this tree diagram, I am brute forcing this all the way through. So again, if I look at each one of these branches, this first branch was 6, 6, 6. 6, 6, not 6. That's 2 6s. 6, not 6, 6. That was 2 6s. 6, not 6, not 6. That would be 1 6. Not 6, 6, 6. That would be 2 6s. Not 6, 6, not 6. 1 6. Not 6, not 6, 6, 1 6, not 6, not 6, not 6, 0 6s. So if I wanted the probability then of x equals 0, that's just going to be this one way of that happening, right? If I want the probability that x equals 1, it's going to be this probability plus this probability plus this probability. If I want the probability x equals 2, it's going to be this probability plus this probability plus this probability. So if I want the probability x is equal to 3, that's going to be just this, because that only happens one way. Does that feel okay to everybody? So I'll consolidate that now. So what I've drawn at the bottom is my probability distribution. So I drew the tree diagram to make it easier on myself to figure out what the probability when x is equal to 0, 1, 2, and 3 is. So I'm able to complete my probability distribution. Does that feel okay? So again, what we did here, not terribly difficult, not that much different than what we did in chapter 8. The vocabulary and the symbols is the part that just takes some time to get comfortable with. The actual process that we're doing here, we're just multiplying and adding numbers. There's no algebra going on. You just have to understand the vocabulary and the symbols and know what you're being asked to do. The process of actually doing it, though, is quite simple. But you really have to think about it. Okay? So the hard part is understanding what you're being asked to do. The actual process of doing it should be easy. Is everybody comfortable here? Okay. Another way we might represent this probability distribution, rather than a table, is you could use like a histogram. So here's a histogram representing that same probability distribution. So the 57.87 is the fraction 125 over 216 converted to a decimal. Everybody's good with this? What's the difference between a histogram and a bar graph?
Histogram together.
Yeah, histogram, the bars touch. There's no gap in a histogram. Unless there's a category with 0 in it, right? Okay. And then just as a confirmation that we've done everything correctly, the last thing that I'd want to do is I want to make sure that those probabilities in my probability distribution all add to give me 1, which is our final check, which they do. Okay. So, again, our basic rules of probability, this is the same basic rules that we saw in Chapter 8. We're just restating them in the terms of a probability distribution rather than a probability model. For any event A, the probability that A occurs is a number between 0 and 1. On your test or quiz, if you give a probability of something less than 0 or greater than 1, what do you get? No credit, right? No partial credit available if you give me an insane answer. Right? Yeah. And just wanting to be clear as to like what my expectation is. Like, it's okay to get wrong answers. I'm happy to get partial credit for wrong answers, but they have to be a sane wrong answer, right? All right. If S is the sample space, the probability of all the events in the sample space has to be 1. In the case of equally likely outcomes, so when we say equally likely, that means the probability that each outcome occurs is the same, like rolling a 6-sided die. But if you're looking at the sum of 2 die, there the outcomes are not the same probability, right? Much easier to roll a 7 than it is to roll a 2. In the case of equally likely outcomes, we can just count the number of ways that A happens divided by the number of ways in the sample space to calculate our probability. Our expected count or expected value is really going to be the same thing as the mean, but it says that given n trials and the probability that A occurs is equal to A, the expected number of times event A should occur is n times A, right? Like, we flipped a coin 10 times. How many times would you expect to get heads? 5, right? If you did 5 times 0.5. If I rolled a 6-sided die 6 times, how many times would you expect to roll a 3? Once, right? 1 out of 6 times 6. Is everybody okay there? All right. And then lastly is the complement rule that says the probability that A does not happen is the same as 1 minus the probability that A does happen. And as we're start doing the things in Chapter 12, here we're going to start running into problems that can only be done using the complement rule. Where last chapter we saw things that were like just more convenient to do it this way. Here we'll run into some things that really, like, realistically you can only do with the complement rule. It's like infeasible to do it without that. Everybody's okay? Again, this should all look familiar. It's just restating these same things we saw in Chapter 8. Maybe with slightly different vocab here. Okay. Yep. And if we want to talk in terms of a random variable, this is just me translating those same statements in the language of a random variable. So again, the probability of x is equal to x. That's any specific outcome for a random variable needs to be between 0 and 1. The sum of all those probabilities in our probability distribution has to equal 1. The one that looks a little bit different is the expectation, or the expected value, or really kind of the mean. Is that it's the sum of x times the probability that x occurs. So in the case of like rolling 2 die and looking at the sum, if I want the expectation of x, I'd look at the x equals 1. Well, the probability of that is 0. X equals 2, the probability of that is 1 out of 36. X equals 3, the probability of that was 2 out of 36. So I'd have 1 times 1 out of 36 plus 2 times 2 out of 36 plus 3 times 3 out of 36. And I add that all up or multiply those all out and then add them all up. And what you're getting there looks very much like a weighted average, right? If you think way back into first semester, it was one of the first tricky things that happened was calculating these weighted averages. It's exactly what we're doing with expectation. It's just kind of like a weighted average. Okay. All right. So the next thing we're going to talk about is a special kind of function on random variables, which is called a cumulative distribution function, or a CDF. So we'll often abbreviate a cumulative distribution function as a CDF. What this function does is it computes the probability for a random variable x that the observed value is at most a specified amount. So when we talk about a cumulative distribution function, it's always an inequality. So we're talking about like the probability that x is less than or equal to some value.
Is that a calculator thing?
It is something that can be done on the calculator sometimes, depending on how it's set up and what you're doing. Okay. So to make this a non-calculator problem, we could give you a table of values like this. This is an example of a CDF. So the probability that x is less than or equal to 0, 0.01. The probability that x is less than or equal to 1, 0.04. The probability that x is less than or equal to 2, 0.12. The probability that yada, 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 x is less than or equal to 7 is 1, because the only outcomes here are the values between 0 and 7, right? Does everybody feel okay? So if I was given this information, I wanted to recover then the probability that x is equal to 1.
Although getting that exact.
Yeah, because right now I have x is less than or equal to 0, x is less than or equal to 1.
Yeah.
How do I get x is equal to exactly 1? Well, if my random variable is discrete, right, because it says this is a student's scaled score on their IA, which is a discrete outcome. You can only get 0 through 7. If I take the probability that x is less than or equal to 0, and the probability that x is less than or equal to 1, if I subtract from x is less than or equal to 1, less than or equal to 0, what I'm left with is just x is equal to 1 is the only possibility. So if I want the probability that x is equal to 6, I can take the CDF for 6 and subtract the CDF for 5, and that'll give you exactly 6.
Gotcha.
Because we've cut off everything 5 or less.
Yeah.
The only thing left are 6s.
Okay.
Does that make sense?
Yeah.
So just, again, trying to connect this CDF, these CDF values to your actual probability distribution. Okay, so again, we've said this earlier, it's now written down, that a CDF is, our function is the probability is less than, or x is less than or equal to some specific value, some specified value. Is that okay? Okay. And this should look a little bit familiar because way back in chapter 5, we talked about cumulative frequencies and cumulative relative frequencies. This CDF function is just a cumulative relative frequency. Okay, if we looked at the graphs, they would look identical. Remember when we say relative frequency, it just means you turned things into from counts into percentages, right? So if I want if I take my CDF, which is my function f, the f of x equals 4 says it's 0.55. That would mean the same thing as the probability p of x less than or equal to 4 is 0.55, right? So we're just using f as our cumulative function, which is the same thing as stating it as a less than or equal to probability. And as I hinted at earlier, if I wanted to find the probability of just one score, like the probability of getting a 5, exactly a 5, or exactly a 7, or exactly a 2, all we're going to be doing is subtracting. So if I want the probability that x is equal to 7, that's going to be the probability that x is less than or equal to 7 minus the probability that x is strictly less than 7. It's okay there? Now, in the case of a discrete random variable like we have here, x is less than 7 is the same as x is less than or equal to 6. Because if it's discrete, there are no values between 7 and 6. Everybody's okay with that? And I can continue this process then to recover the probability distribution from the CDF. Or if I'm given the probability distribution, I can take that probability distribution and generate the CDF from it, right? So if I started here and I want to get to this, these two added together gives me that. These three added together gives me that. These four added together gives me that, right? That I can go back and forth from CDF to probability distribution. If I have one, I can generate the other, at least in a discrete setting, relatively easily. In a continuous setting, not so much. Does everybody feel okay with the relationship between a probability distribution and a CDF? How do we know that that chart below is a probability distribution? What are the two things we need? Every event has a probability associated with it. Check, right? Because every outcome in our table has a probability attached to it. And the sum of those probabilities must be 1, which I can see in the CDF because what is the last number in my CDF? 1. So I could check this also manually by adding up the numbers in the tables and making sure they get 1, but like, unless I did something silly, I know they're going to be 1 because the CDF ends at 1. Is everybody okay there? But if you don't trust your arithmetic, or you're not sure, did I do that right? That's the check. It's just to add up all the probabilities in your distribution and make sure you get 1 at the end. And if you don't, ruh-roh raggy, you made a mistake. Let's look at some examples. So it says when people create codes for their cell phone, the first digit follows the probability model shown below. Okay. What type of random variable do we have here? Discrete or continuous? Discrete. What are the different outcomes in that discrete random variable? 0 through 9, right? There's 10 possibilities, but they are the numbers 0 through 9. Okay, what is the probability you pick a first digit that is more than 5? So what are the numbers that are more than 5? 6, 7, 8, 9. So if I want the probability we pick something more than 5, that would be the sum of 0.067, 0.058, etc., right? Yep.
Quick question. When it says in the homework, like the 12.1 ICEs, what is that? Is that like this stuff?
The in-class examples are the things in the OneNote.
Oh.
That's we'll do that in class. Okay. The ICE is an in-class example. They're not things you need to do as homework.
It wasn't like I just didn't know it was a separate.
Yeah, it's the separate. It's like the practice problems that we do.
Yeah.
All right. So we did that. That's easy enough, right? What if I want to show the probability histogram for this? What am I going to do? Yeah, just build a histogram where the height of the box is the probability, and each box would then be labeled for the outcomes 0 through 9. Everybody's okay here? Pretty easy. All right. Let's talk about expectation or expected values. The expected value for a random variable is going to be the same as the mean. And that's just going to be the average value we'd expect for x over many trials. So let's go back to this probability distribution that we built earlier, where we had one die that we rolled 3 times, and we were counting the number of 6s that we got. So if I wanted to calculate the expected value for this, my expected value formula is x times the probability of x, and then add it all up. So this would be 0 times 125 over 216 plus 1 times 25 over 72 plus 2 times 5 over 72 plus 3 times 1 over 216. Okay, so it's just the outcome times the probability of that outcome, add it all up. Which again, should look familiar because what we're doing right now is really just a weighted average like we did in first semester at the very, very start. Forget if that was chapter like 1 or 2, but it was pretty early on. When we do that computation, we get 1/2. So that would be, what that would say is that on average, if I rolled a die 3 times, I would expect to get half of a 6. Or that the number of 6s I expect to get is 0.5. Which is okay that it doesn't really make sense in the context of the problem, because we do this all the time, right? If we sample a random American household and we count the number of children, you'd expect to see like 1.5 children. It's like, well, that doesn't make a lot of sense. Who has 0.5 children? It's like, oh, I see. We're just talking about like on average, right? All right. Let's look at another type of problem here. It says for the random variable x, we have the probability distribution shown below. We want to solve for the value of c. How do I do this? The key here is that it's told you that this is a probability distribution. So what are the 2 things that we have to have for a probability distribution? Every outcome needs to have a probability attached to it, and the sum of those probabilities needs to be 1. That's the part that I'm going to use to solve for c, because it gives me an equation. So I'd say 7c plus 5c plus 4c plus 3c plus c is equal to 1.
Yeah.
And then I can solve for c. So c is 1 out of 20. So then I can use that to say the probability that x is equal to 1 would be 7 out of 20.
Because 1 is 6.
Because 1 is 7c.
Oh.
So I have 7 times 1 over 20. Or 7 over 20. Et cetera, et cetera, et cetera, right? And then I could build a histogram or whatever, calculate an expectation or whatever I was asked to do from that. I have the full probability distribution, so I can kind of do whatever I want with it at that point. So, what if it asks me to find the probability that x is greater than or equal to 4? How many outcomes do I have that are greater than or equal to 4?
2.
2. Those outcomes are
3C and C.
4 and 5.
Oh.
So that I would add up the probabilities 3 over 20 plus 1 over 20. Is everybody okay with that?
Yeah.
Why?
Okay.
You're good?
So they can raise it.
Okay. What if I wanted the expectation? How do I calculate expectation again?
Oh, you do the 1 times 7.
Yep.
2 times 5. And then
Add them up,
yeah.
right? It's the sum of the outcome times its probability. So I'd have 1 times 7 over 20, plus 2 times 5 out of 20, 3 times 4 out of 20, 4 times 3 out of 20, 5 times 1 out of 20, and then add those all up. Oops. So in the end, I get 2.3. Would be the expected value. This type of problem here is a very common IB presentation in this kind of topic, where they ask you to give you the probability distribution, and then once you have that, answer a bunch of questions from it. All right. So again, expectation is the same as mean. So the next thing we want to be talking about would be standard deviation or variance, which is just the standard deviation squared, right? So again, back from first semester, I think like chapter 4 or something, standard deviation measures the average distance of observations from their mean. It's calculated by finding the average of the squared distances and then taking the square root. So again, way back in chapter, I don't remember, 4 or something, these were the formulas for variance and standard deviation. Right? What we're going to do now is translate these into the language of random variables and probabilities. You guys okay with that? Okay. So again, same thing. Now I've included the mean on there in the same format from previous. Now what we'll want to do is like take these and put them into the language of a random variable with a probability. So our mean is the same thing as expectation. Here's our expectation formula. We've done a couple of examples on that. Hopefully by now you look at that and you recognize which it is you're supposed to be doing. So the variance, these are our x1, x2, xn are our little x's. And x bar is our expectation. Oops, I should go back. Oh, sorry. One back. All right, whatever. It's fine. So we have x minus the expectation. So mu, I don't know why I did that instead of using x bar here, but mu and x bar both mean mean. So does e of x. So we're going to have x, the outcome, minus the expectation, squared, times the probability of x. And we'll add those up each time. And that'll give us the variance. And if I take that and square root it, that'll give me the variance, or the standard deviation, excuse me. Oh, I just went back too far. Right, okay, so let's go back to here. So if I look at this fraction, I have like x1 minus x bar squared over n, x2 minus x bar squared over n, all the way down. So the over n part is the why it's multiplying by the probability there. You can remember probability is like part divided by total. So since we're dividing by total, that's why the probability gets stuck in there. All right. So let's go back to this example that we were looking at. Of course. And let's find the variance, and after that, the standard deviation using this example we've been working in. So I wrote down the expectation that we calculated earlier. Again, this is rolling a dice 3 times and counting how many 6s we get. That was this random variable. Is okay? So this is my formula for variance. So my first term, I'm going to add up, since there's 4 outcomes, I'm going to be adding up 4 things in my sum for variance. So I'm going to take 0 minus a half squared times 125 out of 216 plus 1 minus a half squared times 25 out of 72 plus 2 minus a half squared times 5 out of 72 plus 3 minus a half squared times 1 out of 216, right? So like x minus mean times probability of x. Great. Does that feel okay? So this is just me building a table of doing this, like we did in last semester when we looked at the lists on our calculator and did this inside of a list. It's the same idea. So if I take that last column then, and I add those guys all up, I get 5 out of 12. And that would be the variance for this random variable x that represents rolling a dice 3 times and counting the number of 6s. And if I take the square root of that number then, that would be my standard deviation. So in this case, it's approximately 0.645. Again, I rounded to 3 significant figures unless directed otherwise. Since that wasn't going to be an exact answer, I guess you have left it as the square root of 5 over 12. And that would be correct. But like Dr. Ruski's, probably just prefer the decimal at that point. Let's look at our next example. So a computer store sells a specific type of laptop. The number of laptops sold each day is shown in the table below. X is the potential number of laptops sold each day. Calculate the expected value of the demand. So again, the formula for expectation is outcome times probability summed for all possible outcomes. So we'd have my outcomes here are 0 through 5. They're attached probability, so I'm just going to do 0 times 0.08 plus 1 times 0.4 plus 2 times 0.24, et cetera, et cetera, et cetera. So when I do that, I get an expected value of 1.9. That would mean that on average, the store would expect to sell 1.9 laptops each day. Is everybody okay with what we did to compute that? Again, not difficult, but it's like getting used to a new language, a new notation. The actual, like, how do I do this? Really easy. All we're talking about is like adding and subtracting and multiplying things. So what do I have to do to answer this question is usually the hard part where you have to think about, like, what is this asking me to do again? Like, what does that mean? So if I want now the standard deviation, the first thing I'm going to do is remember what my expected value is. So the standard deviation is the square root of the variance. And to calculate the variance, I'm going to do outcome minus expectation squared times probability of outcome, and then add that up for all possible outcomes. So again, if I do my little table, outcome minus expectation, 0 minus 1.9, 1 minus 1.9, 2 minus 1.9, et cetera, et cetera, et cetera. Square those differences, and then multiply that by the probability. That gives me these 5 partial standard or partial variances. I add them all up to get the actual variance, and then I square root that number to get the standard deviation. So on what does that standard deviation number mean? How can I interpret that? So on any given day, the number of laptops sold on average would be 1.8 laptops away from the mean, or the expected value. So I might sell as many as 1.9 plus 1.8, or 1.28 laptops, or as few as 1.9 minus 1.28 laptops. And it's too early for me to do the mental math to add those things together this time of day. From the sound of it, you guys are telling me it's like we're ready to go here. I'm suspecting the bell's gonna ring here right now. We'll pick this up next time. You can start in on the assignment for this if you wish. We still have some more to do in this section, so if you get to a point where it's asking you to do stuff, you're like, I don't know what it's asking you to do, you can just stop or skip that problem and go on to something that you recognize.
Have a good day, Dr.
Yep, take care.
So are you or no?
Those are not something that are due, that's something we would be doing.
Wow.
Thank you, Dr.
Yeah, because we didn't get to it. If we had, 70 minutes
So
instead
what,
of 8.
all
You can start on the homework problems. If we didn't finish, so if you see something you don't recognize, you can just like skip it or stop or whatever. We still have 10 more slides or whatever here.
Yeah, scallops are really, really so what?
Yeah, I understand. No big deal.